The problem is from GATE 2018 mathematics paper, question number 40. The problem given is, let M2 of R be the vector space of all 2 cross 2 real matrices over the field R, where R is the set of all real numbers. Define the linear transformation S from M2 of R to M2 of R by S of x equal to 2 times x plus x transpose, where x transpose denotes the transpose of the matrix X. Then the trace of S equals. So the NPTEL reference to solve this problem is Module 5, Lecture 19 of Linear Algebra. The title of this lecture is The Matrix of a Linear Transformation by Dr. K.C. Sivakumar. He is from Department of Mathematics, IIT Madras. Even you can watch this reference video using this YouTube link. So now coming to the solution, you can see that it is asked to calculate the trace of S, where S is the linear transformation from M2 of R to M2 of R. Since here it is linear transformation and it is difficult to calculate the linear trace of this linear transformation directly. So what we do is we write the matrix representation for this linear transformation. Then we calculate the trace of S in the trace of that matrix which represent this linear transformation, and from by just adding the diagonal entries of that matrix. That will be easier. So for that, firstly let me write, it is given that M2 of R is the set of all 2 cross 2 matrix such that with real entries. Then this forms a vector space over R. And yes, from M2 of R to M2 of R defined by S of x equal to 2 times x plus x transpose, where x is in M2 of R. Yes. So then it is asked the trace of the linear transformation. Yes, the trace is nothing but the sum of the eigenvalues. So first we have to calculate the eigenvalues of this linear transformation. That is the usual method. But since it is difficult to calculate the eigenvalues and eigenvectors, so what we do is we just follow the matrix representation of this linear transformation. And for that we have to assume two bases. One is for domain and one is for codomain. Since here both are same, I mean the domain and codomain, so I just assume one basis for this M2 of R, and which is nothing but the standard basis. And we have the standard basis as 1001, sorry, 10000 and 0100 0010 0001, and this is the standard basis, is a basis for M2 of R over the real field R. So then we have, so how we have to write the matrix representation of S with respect to this basis is, so we have to, by considering each vector in this set at a time as x, so we have to find the image of this each vector in this set, basis set, and we have to calculate the image of that vector under this linear transformation S, and again we have to write that image as a linear transformation of these four vectors again. And when we write that scalars of that image vector, when we write as a linear combination with these four vectors and in column as a column vector in one matrix, and finally we get that matrix as the matrix representation of this linear transformation. Yes, so that follows as the following way. So firstly we have to look at the image of this vector under this linear transformation, and that vector has to be written as a linear combination of these four vectors. So firstly I am assuming S of 1000, So this is nothing but 2 times 1 0 0 0 plus by the definement of the linear transformation, yes, this we get as this, and this is nothing but in total 3 0 0 0. And similarly the and this we have to write as a linear combination with these 4 vectors again. So that can be written as 3 times 1 0 0 0. And again I'm considering the second vector in this basis, and I have to calculate the image of this vector with respect to the linear transformation. So for that I am considering the second vector. So we get this as 2 times 0 1 0 0 plus 0 1 sorry 0 0 1 0 as by the given linear transformation, and this we get as, and we can see that this is already in the linear combination with the basis elements as sum of as a linear combination with these two vectors. So we don't need to write this in any another manner again. So first and thirdly, I have to calculate the image of the third vector in the basis element with respect to the linear transformation. Then we get this as 2 times 0 0 0 1, sorry here 1 0. So we get this as 0 0 1 0 plus the transpose of this matrix, that is 0 0 sorry 0 1 0 0, and again we can see this is a linear, this is already in the linear combination with the basis elements as a linear combination with these two vectors. So finally we calculate the image of the fourth vector as s of 0 0 0 1, and this is we get as 2 times 0 0 0 1 plus 0 0 0 1, and this is in total 3 times 0 0 0 1. So now what we have to do is the matrix representation of the matrix representation of the linear transformation with respect to the standard basis is given by the matrix, the 4 cross 4 matrix, where the columns of this matrix are nothing but the scalars. When you the scalars of the image vector, when you write that vector as a linear combination with this basis, so that is we have the first image as this, and it is already in the linear combination with these vectors. So I'm writing this vector as the linear combination 3 times the first element, 3 times the first element plus 0 times second plus 0 times third plus 0 times fourth. So I'm writing that order in the column vector as 3 0 0 0. And coming to the second vector, we can see this vector is in the linear combination with these 4 vectors in the order 0 times the first vector plus 2 times the second vector plus that 1 time that vector plus 0 time fourth vector. So that I am writing in the order as 0 to 1 0, and similarly for the third vector, so it is as a linear combination 0 times the first vector plus 2 times the third vector and 0 sorry 1 time the second vector and 0 times fourth vector. So we can write this as 0 1 2 0 0 1 2 0, and the third vector, the image of the fourth vector, this is already in the linear combination with the 4 vectors in order 0, 0, 0, 3. And this is the linear transformation. Sorry, this is the matrix representation of the linear transformation with respect to the standard basis. When you keep changing the when you keep changing the basis for the domain and codomain, we'll get you'll keep getting different matrix representations. But all such matrices have same properties such as basis, determinant, etc. So since here it is asked the trace and whatever the basis you consider for the domain and codomain, we'll always get the same trace. So here we get a trace of S is nothing but the sum of the diagonal entries. And the diagonal entries are nothing but when you have a square matrix, the elements in this order, in these positions are called the diagonal entries. That is 1 cross 1 entry and 2 cross 2. I mean the second row, second vector, and the third row, third column, fourth row, fourth column element. These are called the diagonal entries. And here we get this sum as 3 plus 2 plus 2 plus 3. And this is nothing but 10. Means the answer is 10. That is the trace.